All right, hello. This is pre-calculus, section 5, chapter 5, section 2. We're going to talk about one-to-one and inverse functions today. The first learning objective is to determine whether a function is one-to-one, and we've been working on this skill since Algebra 2. So if you have one item, your input mapping to one distinct output, you are one-to-one. A function is one-to-one if any two different inputs in the domain correspond to two different outputs in the range. That is, if x1 and x2 are two different inputs of a function f, then f is one-to-one if f of x1 is not equal to f of x2. So we look at these two. One-to-one means this one state maps to this one population. Not one-to-one means this dog maps to 11. Also the cat maps to 11. So when x1 maps to a specific y1, that is not equal to any other y's. And then we see that these are not one-to-one and this is not one-to-one. Okay, so when we look at the first one, this guy is one-to-one because we have just a distinct input gives you a distinct output. So we were asking ourselves previously if a function, if it's a function, you have to pass the vertical line test. But in this case, we're restricting that down just a little bit more and saying now we can't share outputs. This is a function, but this is not one-to-one because I have x2 going to y1 and x1 going to y1. So the second one is not a function. And then this one definitely is, this is not a one-to-one function. It's a function, but not one-to-one. This guy is neither because the x1 inputs to y1 and y2. So this is not a function, nor is it one-to-one. All right, so we're going to simple basic determining whether a function is one-to-one. We look 55 and 61 share 38, so we can automatically say heck no, tech no. On B, we look input -1, -2, -1, 0, 1, and 2. The outputs are 6, 3, 2, 5, and 8. Nothing overlaps, nothing repeats. So this is one-to-one. Horizontal line test. So every horizontal line intersects the graph of a function and at most one point, then the function is one-to-one. So we did, for functions, we did the vertical line test. For one-to-one, we're going to do a horizontal line test. Like so, we throw down our horizontal line and we move it up and down, and we see that this touches more than once. So this is not one-to-one. All right, so let's look at a parabola. Is a parabola one-to-one? No, it does not pass the horizontal line test. Cubic function, our little swimmer guy, is he one-to-one? Yes, because he passes the horizontal line test. A function that is increasing on an interval is a one-to-one function. A function that is decreasing on an interval is a one-to-one function because if you're increasing, your values are changing. You're giving a new input and getting a new output, and as they increase, they're increasing. Same with decreasing. If I am going down, then the next xi input will give me an output that's less. So we're not going to get any repeating ones. We're going to determine the inverse of a function defined by a map or a set of ordered pairs. This is mega easy. I love inverses. Makes sense. Life is good. So we're going to suppose f is 1 to 1. In order for an inverse to work, you really need a 1 to 1 function. Then to each x in the domain of f, there is exactly one y in the range, because f is a function. And to each y in the range, there is exactly one x. So the correspondence from the range of f back to the domain is called the inverse function of f. So an inverse function takes your y value and traces it back to your x value. It takes your output and traces it back. So it is, in fact, the opposite of whatever your original function is. So when you have input and output, to find the inverse, you just switch them. So then your output becomes your input and your input becomes your output. This works for coordinates as well. Then you can look at your range becomes your domain, and your domain becomes your range. So we switch the x and the y. So the inverse of this, I'm going to, instead of having -5, 1, I'm going to have 1, -5. Instead of 3, 3, I'm going to have 3. Oh, instead of 0, 0. Oh, okay. Instead of 2, -4, I'm going to have -4, 2. Instead of 7, -8, I'm going to have -8, 7. So then the domain is just all your x values ordered, and your range is all your new y values put in order. So the domain of your original function is the range of your inverse function. So everything just switches. So if you look this little to the -1 power, we're going to use that to identify inverse. So if we have f of -1, that's technically the inverse of f. So it's not, we're not raising it to the -1 power, we are just saying it's the inverse. So it's a little, instead of writing the words inverse, we're just putting a little -1 power. The domain of f is the range of the inverse function, and the range of f is the domain of the inverse function. So they just switch. All right, so check out the way we write this. The inverse of f, when I put my original function into the inverse, I get x. When I put the inverse into my original function, I get x. So for example, if I have my original function is 2x. My inverse function is 1/2 x. So if I put in 2x into 1/2 x, so instead of an x, I have a 2x. The 1/2 and the 2 cancel, and I get an x. Vice versa is also true. If my inverse is 2x, and if my original function is 2x, and I put in 1/2 x, I do that, I will get out just x. So this is a way to test if you have the true inverse. If you plug in the original equation into your inverse, and you get just x out, everything cancels, then you have an inverse, a true inverse. Okay. So we verify that the inverse of g of x equals x cubed is the cubed root of x. And if you notice, opposite of cubing is cube rooting. That's on purpose. By plugging in x cubed for x in our function. So the cubed root of x cubed is x. Okay? And then we do the opposite. We put in the cubed root into our cubed function. So if we take cubed root of x and we cube it, we get x. So we can say that these two are inverses. We can do the same thing here with 2x plus 3 and 1/2 x minus 3. If I put in my inverse function, I take out the x and I put in 2x plus 3. I get 1/2. 2x plus 3 minus 3. Plus 3 and minus 3 cancel. 1/2 times 2 is x. Then we have 2 times 1/2 x minus 3 plus 3. So the 2 times the 1/2 gives me x minus 3. And the minus 3 and the plus 3 give me 0, and I'm just left with x. Okay, so we're going to verify that these are inverses, 3 over x plus 5 and 3 over x minus 5. So when I plug in, we have to note x cannot equal -5, nor can it equal 0, because that is not in the domain of our function. So when I take out x and I put in 3 over x plus 5, 3 over x plus 5 dividing by a fraction is the same as multiplying by the reciprocal, so I'm going to multiply it by x plus 5 over 3. 3 and 3 cancel, and I just get x plus 5 minus 5. Plus 5 and minus 5 cancel, so I just get x, as long as x does not equal -5. We do the opposite. We take out our x here, and I put in 3 over x minus 5. My minus 5 and plus 5 cancel. 3 divided by 3 over x, dividing by a fraction, is the same as multiplying by x over 3. And if I multiply by x over 3, the 3's cancel, and I'm left with x, as long as x does not equal 0. Okay, we're going to attain the graph of the inverse function from the graph of the function. And we do that by switching the x and the y coordinates. When we do that, we essentially reflect that coordinate across the line y equals x. So the graph of a function f and the graph of its inverse are symmetric with respect to the line y equals x. So here, I have here, if I fold, and then I actually do this quite often, is I fold it, the line y equals x, and then you can retrace the inverse. This also works by picking coordinates and switching the x and the y values and then graphing those. All right. So the graphing the inverse, the graph of figure 16a is 1 to 1. And we're going to draw the graph of its inverse. So I'm going to take each of these coordinates, flip the x and the y, and graph them. So I'm going to graph 1, 2. I'm going to graph 0, -1. And I'm going to graph -1, -2. When I do that, I get the inverse. Easy peasy. All right, so now we're going to find the inverse when I have an equation. The best way to do it, I don't prefer graphing, but you can. You can graph. All you have to do is replace f of x with y. So we get y equals 2x plus 3, and then switch the x and the y, because what do we do when we want to graph the inverse? We switch the x and the y. So to obtain the inverse from the function, we go y equals, we switch the x and the y, solve for y. So I'm going to minus 3 from both sides and divide by 2. So the inverse is 1/2 x minus 3. You can check your answer by plugging it into the original function and making sure you get out x. You can also check by graphing if the inverse and its function are symmetric with respect to the line y equals x, you know you have a winner. All right, so to recap, you replace y with f of x, then you switch the x and the y. Our new equation defines the inverse function. If possible, solve the implicit equation for y in terms of x, and then check your solution. All right, a little bit harder. We got a numerator and a denominator. So we replace y, and then we switch the x and the y and try to solve for y. So I multiply both sides by y minus 1. Then I distribute the x. Then I add x to both sides. Then I distribute out or factor out the y. And I'm going to divide by x minus 2. So the inverse is x plus 1 over x minus 2. A little bit tricky algebra going on there. As long as x doesn't equal 2, this is the inverse of the function. Then we want to check it. So we're going to plug in 2x plus 1 over x minus 1 and make sure when we do that operation on it, we get out just x. And remember, x cannot equal 1 because it makes my function 0 in the denominator. All right. Sometimes in order to get a one-to-one function, you have to restrict the domain. So like if you have a parabola and you want to find the inverse, you have to specify that you're going to be greater than or equal to 0, so it just gets half of your smiley face. So when you do that, the process works just the same, but you have to keep your domain the same throughout, so that you're restricting it. So we are just taking this right-hand side of the parabola. So when we do the inverse, we just inverse that right-hand side. And that's it.